Okay, nice. Hello? Okay. All right. So, hello, I'm Juan Conejero from Runtime Verification. I'm a security verification engineer. And today I'm going to talk about, well, the work regarding security that we do at Runtime, so auditing and formal methods. So we'll be basically going through what's an audit like at RV. We'll be giving a brief introduction to what formal verification is, then the history of runtime verification and formal verification, and finally our current approach to formally verify AVM-based smart contracts. So we are a security and formal methods company. We do, of course, security audits and formal methods engagement in the blockchain space, but also have done it outside of the blockchain space in the past. The work actually that we have done with the Blockswap and the PON team, it's been quite extensive. We've audited several protocols of them, but of course they have also partnered with other companies to further their protocol security. So auditing, right? So what's auditing really like, and how do we do it at Runtime Verification? So basically, auditing at its core, it's a line-by-line review of the code base of your protocol, right? It's important that the person doing such review should be free of bias, but basically, it's at the very core of the process. It's the cycle of reading the code, asking questions, and answering them, or at least try, and go back again. So, and by asking questions, I mean this is where we fall like traditional security questions, reentrancies, off by one's errors, or all this sort of stuff. Also, like, I mean, these are like the more generic ones, right? But also protocol specific. The problem with this cycle, I mean, this cycle can get you like quite far actually. But the problem with this cycle is that it can also get you only so far. So there are two major pain points to this cycle, which is what if you run out of questions, or what if you run out of ways to find answers, right? At some point, you may just look at the code and see no more problems and everything looks good, or you may have questions, but the answers you can come up with or the feedback that you're getting from the team for some reason doesn't tick like all the boxes. So once you're here, like what is a good way forward? So in Runtime Verification, we used formalisms, and we use especially models, invariants, and tools to basically exit these sort of like pain points when auditing. So let's go over them. So a model, first of all, it's model. So a model is just a representation of the system. And a representation is just a description in some language. So depending on the language that you choose to represent the system, you will end up with different kinds of models, such as code models, which are, you somehow program again you can program again the protocol, and then, you put yourself in the developer's shoes, and then you have to do like some implementation decisions and so on. And well, basically, it's a nice way of understanding again the code base. If you look at, you notice some difference between what you have done and what the protocol is, you can justify them and so on. Also, like math models. So basically, you just throw away the implementation and you focus on like the most important, like the most abstract part, and then you can do some sort of rigorous analysis. And then it's like pseudo models, which because I mean, the main goal of all of these tools is basically to allow you to peer deeper into the protocol. So sometimes it doesn't pay off to be extremely formal, or to reproduce large parts of the code base. So we also use like pseudo stuff, like pseudo math, pseudo code, if it fills the bill, because it may only just work for you, and then you don't have to spend any more time on that. And then regarding the elements of the system that you want to model, it can be either economic, so does it make sense, what the economic equations that are in place, or more like game theoretic, what are the kinds of incentives, what are the users incentivized to do, or what are they allowed to do, and try to find some sort of like hidden allowed places for behavior to occur that it may not be good for the protocol, and also like plainly code related, so implementation wise, like why did you choose to do it this way, other ways of organizing the protocol, and so on. The second one is invariants. So invariants are just properties of the protocol. So it's basically you go through the protocol and you try to list what are the things that should always hold for the code. And this can be, for instance, code invariants, like what are the relationships between these two variables, what are the properties that the elements of the array should fulfill, also like. But these are like more specific to the implementation itself, and protocol invariants, user level invariants. So like what are the core properties of the protocol, or what are users, right, like allowed to do. Now, once you have invariants, then you have a very nice description of the system. It's not a model, but it's a very nice list of things that never should go wrong. And then you can try to prove them more or less formally in a pen and paper proof, or you can try to convince yourself hard enough that they hold. And this is also like a very nice way of looking again at the code, even though you've spent like a lot of hours in it. And it usually yields very nice results. And finally, we have tools, which is once you've gone through models, invariants, you have thought of very esoteric scenarios, then you can turn it into tools and rather try to code these esoteric scenarios, try to poke at equations you're not so sure they hold. And there's like there are a variety of tools to choose from for where to further your analysis on the code so far. So nice. The audit is done, so what do you get from an audit? So basically you get a POB, which is this term I made up, which is a proof of bug. So basically you get a nice report that says, here was a bug, here was a bug, here was a bug. This is something you may think about changing, or then you also get along like whatever the formal device that the auditors choose to do to peer deeper into the code. And then we also try to document quite thoroughly what we understand the protocol is. So this, in my opinion, is something very important. We always try to depict what is our understanding. So it's also like a blueprint of, okay, the auditors understood this part of the protocol in this way, which, I mean, it usually aligns very much with the developers, but it's a very nice source of documentation. But the thing is, what you don't get is a POB, which is a proof of no bug. So in this paradigm, you will always get proofs that things go wrong. But very rarely you will get proofs that things go right. I mean, you can have proof of invariants, but this, at the end of the day, I mean, they do increase a lot the certainty that, that your code is doing fine, but at the end of the day, these are pen and paper proofs, and if you change the code a bit, you should redo them a lot, and it's not a trivial work. And at the end of the day, pen and paper proofs, you cannot trust them 100%. So, if you want to increase your protocol security, if you want to get out of this paradigm of proof of no bug, you can turn to formal verification, which is basically how to get a proof of no bug. So the most important part of formal verification, and this is the most important property everyone should be aware of, is that it sounds fancy, and you should do it in your protocol. But for real, so high-level description of what formal verification is proving the correctness of a program or algorithm using formal methods. And here by proving we mean, for correctness we mean, we need to verify to define what correct means, right? So this means defining what truth is. And this falls into the hands basically of the protocol people. I mean, we do write specifications, but it basically means that you need to say what is correct for the code to do and what is not correct for the code to do. And this is the most crucial step because, as you see here, like the code will be as good as your specification. So if you miss a case, if you are too ambiguous, if you, for some reason, just encode a bug, God forbid, you can only prove that that is what your code will do, right? And then, so once you have like this very thorough, exhaustive description of your system in some formal language that it's code readable and so on, then you can prove it. And by proving, I mean, that's a Pandora's box, but basically there are a number of, there are quite some techniques that allow you to claim that you can prove that your code does as your specifications. Those are usually hard to carry out, but it's also important to understand that proving that your code does what your specification does will not uncover any bugs in the specification. So if your specification is correct and you prove that, that your code does as the specs, then you can say that your code is correct. If you had wrong code and good specifications, then it's where the fruits of formal verification come, because you will find during the proving that your code is actually wrong because it doesn't conform to the specs. So you always get a proof of no bug relative to what you specify no bugs are. There are a number of tools that allow you to carry formal verification for Solidity, AVM, smart contracts. So great. Now we know what formal verification is. So, but where can you apply formal verification in a protocol? So there are basically these layers here. So you can apply it to a modeling level. So say before you even write any line of code, you can just think what what your protocol is supposed to do, and then you just write a very thorough specification about it. And then you list a bunch of theorems or properties that your design should have, and then you prove them, and you will have a very nice protocol specification. You can verify that your specification holds certain properties. Then you can also verify source code, and you can verify bytecode. The advantage of verifying bytecode is that you skip also this compilation step, which may introduce bugs from the compiler. So great. Now that we know what's formal verification, what have we done at runtime verification about formal verification? So we have done, well, in the blockchain space, I've done a number of verifications, like most notably the Ethereum deposit contract. Outside of the blockchain space, we have also done extensive formal verifications with several clients. Our approach to what's formal verification, because at the end, now we know we want to prove stuff, but how do we do that? So our approach is based on the K framework, which basically is a semantics framework that allows you to specify the semantics of your programming language in this framework. And basically, once you get the specification of your programming language here, you will have derived automatically for you all these tools that allow you to, well, for one, compute, do basic execution of your programs. But the important thing for us is that we also have a symbolic execution engine and a deductive verifier. So just by defining the semantics of your programming language in K, that immediately allows you to perform formal verification on your programming language. But there's also a number of benefits as listed here, so that you only need to update one tool and so on, but this is more specific to like more general concepts. For what we're concerned, the important thing is that by defining your semantics, you get formal verification for your programming language. So now we turn to KEVM, which is basically we take this nice framework in which we only need to define semantics to get very nice things, and we apply it to the Ethereum virtual machine. So this is what KEVM is. It's just the K semantics of the Ethereum virtual machine and its derived tools. So we have the equivalent of the yellow paper here in the yellow paper. This is a paper which is automatically generated from the K specs. Here's the GitHub, and basically we pass the same conformance test suits as everybody else. And yeah. So this is what specifying stuff in K looks like. Not ideal for a working programmer. Not because you cannot learn it, but because it's a mouthful and takes time. So this is basically the specification of the balance of function, which says if I give you an address, you should give me this storage slot, right? And if this is really not the full spec, so this is the full spec for the balance of function, so it can get quite heavily. Luckily, you don't need to interface with this anymore, because we have used Foundry's ease of use to define parametric tests to basically translate your Foundry test, your property-based Foundry tests into KEVM specs. So basically, this means that you now can formally verify, symbolically execute your Foundry property tests. Basically, the way this works is there's this very well-known language, Hora triples, to do formal specifications, which is basically you assert some preconditions about the code, you assert which part of the code you're going to execute, and then you assert what preconditions you expect to hold at the end of execution. And basically, you can emulate that pretty closely, or basically, with Foundry property testing, which is with the variables, when you define what would be the fuzzing parameters in a classic Foundry property test, it now become symbolic parameters. So you are first declaring which are the symbolic parameters of your spec. Then you are initiating what's the pre-state of your execution. What are your assumptions on how the state is? Then you execute your code, and then you assert some post conditions. And basically, what KEVM will do if you symbolically execute this test is a guarantee that anytime you have these preconditions, you execute the code, you will always end up in this state, in the post state. This has well, a number of advantages. So it's strictly stronger than fuzzing, since fuzzing tries a bunch of stuff, but ultimately if it says it's okay, you cannot know for sure because there's a pretty big space to fuzz. You have it's easy to use now because you don't have to interface again with K. It's open source, so anyone can go and learn how to do it. Actually, we have quite some nice tutorials, so please, we urge you to do it. You can reuse tests because at the end of the day, you're still writing Foundry property tests, right? So you can still fuzz over these tests. These are also good targets for symbolic execution because symbolic execution is not only symbolic execution executing Hor triples. I mean, you can symbolic execute like a lot of things in a lot of ways and try to answer a lot of questions with this. So this is a nice way of narrowing down your expressive powers on what do you want to symbolically execute and what do you want to check. But it's expressive enough so that you can actually specify your system in it. So it's a very nice balance compromise between expressiveness and power of verification. And it's also integratable into CI. So, I mean, since these again are just like Foundry property tests, for instance, a nice workflow would be you code all your invariants in this, but you don't want to. I mean, symbolic execution is strictly slower than fuzzing, so you don't want to symbolically execute every time you, for instance, make a commit to your code base. But you can run fuzzing over it, and every time you're doing like a minor version or a major version, you can still exercise the symbolic execution of your code base. So, and there are some limitations currently. So performance is, as I said, symbolic execution is not the fastest. And user experience, this is a new technology interfacing Foundry and KEVM. So there are some edges to polish, but we're currently, so we're improving in both ends. So within 2 months, we've gotten more than a 10x speed. We're also implementing flexible execution options because when you're verifying, it's not only this gear and then go forward, so that's very nice. And in user experience, we're actively listening to our users' feedback, and there's a number of exciting features coming with regards to how pleasant it is to use our system for proving, making it more interactable with the user and so on. It's not over yet because I still have 3 minutes. So let's go through an example, basically very quickly. So just to show like how, because now you can say, oh my God, yeah, but still it's symbolic execution and the slides I showed about K are terrible and what are you going to do? So this is a very simple contract. Basically, you have it's a set number. So if your number is not coffee and you are not in lock, then it will update. But if you are in lock and your number is coffee, it will just revert, right? So basically, the intended specs for this simple function is as simple as you feed it a uint, and then whatever boolean you want, and the counter that it sets, it should be the integer that you feed it, right? And I mean, we can all see that if, in case you have here 2 cases, in case you fulfill these conditions, then you will revert. So how do you execute this? Well, first you would go to the terminal, you would say Foundry compile, and then the thing will compile. And then you would say KEVM Foundry proof, that's the test, name of the test, and then it will fail because we know it's doomed to fail. And then you can ask it for failure information. And the important bits is here. It will say the test fails, and here's this path condition that makes the test fail, right? Still, this is not the ideal way of working with a very complicated tool because it's only command line based, right? We would like something more visual, such as this. So we have this visualizer in which you have on the left-hand side, you have the nodes, which is basically the picture of what your program is, how your program is executing. Then you have the EVM state. This is plain K because this is how we encode the semantics. But it's not that hard to read. It's very hard to write. I mean, if you have to write something, but if you want to interpret what's happening, this is more feasible. Here are some constraints on the current node, on the current state of execution, and here is some mapping to the source code that you're executing. And then basically, at the end of all of this, what you would interpret that, what KVM would give you to interpret that as the symbolic trace of the execution would be like this tree-like. And so this is basically how you would encounter that there is a case that indeed it reverts in this execution. Then you can apply this to more complex scenarios and so on. But basically, the way you work with this, it resembles very much like this. So yeah, now I'm done. So thank you for attending this talk. Yes, there is a birthday today, yes. Oh, okay. And it happens to be mine. Oh my God. Happy birthday to you. Oh. Happy birthday to you. Happy birthday to you. Thank you. Good thing that I like to be the center of attention. So are there any non-birthday related questions? Okay, take me pictures because I'm hilarious. You should either try our KVM tutorials, documentations, and or Discoin and tell us either how we could improve, and we will do it for free. Okay. Yes.
So are there some examples of classes of invariants that are notoriously very computationally hard or unfeasible? Like there are instances that say, hey, this is really an invariant that is usually don't tackle in this way because it's going to be a computational nightmare, or?
So more than invariants per se, I would say currently what we are devising is a particular. So as I said, this is like interfacing K with Foundry. It's quite new. So but what we are seeing is rather than invariants, it's more like how you write your tests. So ideally, would like you write your Foundry property test the way you write your Foundry property test. You don't care about it, and then you symbolically execute it. What we're seeing so far right now, and this is one of the edges we want to solve better, is that you need to do some massage to your regular Foundry Foundry test to get there. But as particular invariants, I don't think so. It comes more to also how complex the protocol is, what kind of how many branches of decisions do you have, and so basically and actually massaging the tests so that are more runnable comes down to say, okay, so how, because when you for instance do a setup function, right, you don't care very much how much branching there is in there on whatever, and it's more okay, do it in the same way that it's sort of semantically equivalent, or that if you're sacrificing something is not dangerous in any way, but that it gives you a more
So do you envision in the future developing probably the equivalent of a set of tactics to basically be able to rewrite tests in a more ergonomic way?
You mean extending the Foundry?
Like for instance in CO2, right? You have tier improving, and then they came up with tactics.
You mean having a tactic language with?
Avoid the total nightmare.
So that's a very good question. So we are aiming at making K and KVM a more interactive theorem prover kind of way, because right now so for instance what you can have is KVM at some point fails and you see it's because it's not seeing some kind of reasoning, and then you say, okay, but this is true, and then you add it as a lemma, right? And then KVM now knows how to do this reasoning. So what we would like is to optimize that in a way that really feels like an interactive theorem prover, and that it's more like a back and forth of, and also in computation time. I computed up to here, and that there is some way of saying, hey, I don't need to recompute symbolically all of this, and so you can have a more one-on-one conversation with the prover. So there definitely, I don't think it will be in a form of tactic language, but definitely there will be some interactivity. I mean, not some, but we would like to have it to be heavily interactive the way you do the proving. Thanks for the question. So if there are no more questions, thank you very much for attending.